Hello, welcome to Converging Dialogues. This is Xavier Bonilla. Okay, well, it has been a long and interesting 4 years. I was looking at my data, and I started the podcast 4 years ago, first or second day of November 2020. And it's been pretty remarkable that I am still going. It's one of those things, as I've said elsewhere, and I'll just say it here as a reminder. During the pandemic, it was a tough time for everyone. And I was consuming a lot of news and information, and I wanted to find a way to kind of put something else in the world and not just consume things. I enjoy writing. Of course, I'm a bit of a perfectionist with it, and I always think it can be better, and it just takes me a long time. And so kind of got frustrated with trying to do that. And so I said, maybe a podcast is a good idea. Talk to people of different ideas, engage in different ideas sincerely. So that's what I did. I kind of did it on a whim. Just one weekend, got some basic recording materials. I've upgraded since, and always tweaking on that side of things. And I have great people that help me. But it just, I've done different ideas. I do like the, me interviewing, talking, having a conversation and having a guest that is specialized or is an expert in a certain way. But I've tried to do other things as well in terms of with writers or with artists or things like that. And I'll probably do more of that, but really tried to stretch myself and see different topics and different things, and really just getting people exposed to different ideas, really for things that aren't maybe talked about as much, or maybe they're not hot in the news. They're really uplifting and kind of pushing people that are doing fabulous work. And so, yes, I've been very, very fortunate to have some people that are well esteemed in society. Either they have some kind of prestige. They've won, a Nobel Prize. They've, been widely published. Some kind of accolades, and that's very nice. I think it's great for them, and I think it's great for the podcast too. But really, my emphasis is on focusing on the work of people and what they're doing. So, my interests are, as listeners will know, are pretty wide and varied. I have a lot of interest, and I'm never going to be a historian. I'm never going to be a physicist. I'm never going to be an economist. And so to me, it's the next best thing. Read the material, talk with folks, ask good questions, but I just want to get the best version of the person on the podcast. I want to make sure that I'm understanding their viewpoints, understanding how they're reading the data, understanding what makes them really passionate about things. And that's my agenda, is just whoever's sitting across from me digitally. I don't really have an agenda, as listeners will probably know. And to be honest, I quite dislike folks that, kind of just have one or two topics and they just hit that hard over and over and over. I mean, that's fine for people to have their passions. That's great. But I really, really want to try and listen and hear and learn from different types of people with different interests. And so I appreciate everyone that's been along for the ride. I have no plans of stopping. I plan on keep going. Sometimes I'm doing, 2 episodes a week. Sometimes it's 1 episode a week. I'll probably keep it about that rate. Might change. But I found a pretty good rhythm at this point and some really wonderful ideas and guests. And I think it's a great way to stay engaged with things in a healthy way. And I, of course, appreciate everyone's support. People that message me, people that subscribe, people that contribute. I mean, it's really, really, really something to know that people around the world listen to my voice and hear my rambling and my thoughts, but really they get to listen to some pretty wonderful people that are doing good work in the world. And I'm going to keep doing that. And I'm glad that it's very helpful for everyone. And so the best thing is really hearing people tell me how much they enjoy it, how much they get from it, that they support the podcast and myself and the folks that are on it. All of that means a lot. And so, yeah, keep sharing online, telling your friends. There's a lot of podcasts out there. So hopefully after 381 episodes, you have realized what this podcast is about, what the style is, and find it something that is regularly in your queue. So appreciate all of the support, and here's to more and more years. With that said, I am very, very happy to bring the conversation I had with Mario Livio. Mario is an astrophysicist, author, speaker. He's also a fellow at the American Association for the Advancement of Sciences. He's widely published. He's published over 500 scientific articles and has made significant theoretical contributions to topics ranging from cosmology, supernova explosions, black holes, extrasolar planets, emergence of life in the universe, and many, many other contributions. He's received numerous awards and recognitions for his research, and he is the author of many books, including the most recent book with Nobel laureate Jack Szostak, Is Earth Exceptional? And that's the book that we talk about. We start by defining life. It's actually a hard thing to define. What is life and what it isn't? We talk about, are we alone in the universe? We also talk about the importance of telescopes for showing us galaxies and what they can tell us about other planets or exoplanets and life maybe out there. We talk about the goldilocks zone, which is where Earth is in this kind of space where we're not too hot, not too cold, and okay for life. We talk about how life began on Earth. We talk about proteins and genes and what the building blocks of life might look like on other planets. We also talk about heat from tidal forces on planets, exoplanets, UAPs, formerly known as UFOs, intelligent life out there in the universe, and many more topics. I love physics and really was excited to talk with Mario. He's brilliant and quite exceptional and such an engaging guest. And so I was very, very happy talking with him about all these wonderful things. Really, really enjoyed my time with him. As always, you can find this conversation and all other conversation at Converging Dialogues at substack.com. I'm also on YouTube, so like, subscribe, share widely with your friends, share on social media, all the wonderful things. And now I bring you Mario Livio. I'm here with Mario Livio. Mario, thanks so much for coming on the podcast.
Thank you for having me.
Yes, absolutely. So you have written a book, co-authored with Jack Szostak. The book is called Is Earth Exceptional? The Quest for Cosmic Life. This is out through the wonderful Basic Books. And this is just a superb book. Before we get into it, I want to see for you to tell people who you are, kind of professionally, academically, all the relevant details, and what you're currently working on.
Yes, so I am Mario Livio. I'm an astrophysicist. I've been throughout my entire career an astrophysicist. I worked for 24 years with the Hubble Space Telescope. I've published many scientific papers, probably 500 or thereabouts. I've published 8 popular science books, of which this is the 8th, just appeared. Others were also on, generally are on either astrophysics, cosmology, and so on, but again, popular books or about mathematics, because I'm a theoretical astrophysicist, so of course I like mathematics too. So a few are on popular mathematics. That's it, basically. On what am I working on now? I mean, I'm still very, very interested in life, namely, in particular, now life elsewhere. Well, of course, as well as the origin of life on Earth. So I still publish the occasional paper on that. And, like I said, this book has just appeared. So I usually start also thinking about my next book which I still don't know what it's just going to be about. And even if I knew, if I told you, I'd have to kill you. So,
are you teaching anywhere or researching anywhere with any institution in particular?
I'm not teaching formally, but I give, of course, many talks at many places. And since I retired from Hubble, I was offered various adjunct professorship positions at various places, which include the University of Nevada, Las Vegas, where I was just there 2 weeks ago and gave a couple of talks, and the Weizmann Institute, where I'm a visiting professor, and so on. So I visit these places, give talks, but I also give many talks in various places. And work on books, as I say.
Yeah, that's fabulous. So the question here for this book, which is really interesting, is about life itself, and more particularly life, outside of this planet. I guess the really hard question, or what I understand to be a pretty hard question from talking to a few other people, is how do we have a good operational definition of life? And so I think when people think about that and they say, well, life is, you're living, like, yeah, you're just living and breathing. But it's actually pretty difficult in terms of how you actually define it. So yeah, how do you answer that?
So you're right. I mean, there have been, of the order of 100 or so different definitions of life. And I must say that we, namely my co-author Jack Szostak and I, did not find most of the attempts to answer that particular question especially useful for our work. But I would say one thing that is clear is that this is a system, an information system, which is capable of Darwinian evolution. And by that we mean Darwinian evolution not at the level of species turning one into the other, but even at the molecular level. I mean, that certain molecules turn out to be more useful, more productive, and so on, and those take on. So I think that a definition of something like this, a chemical informational system that is capable of, transferring that information from one generation to the next, that is the closest, I guess, we could come to a definition of life. Now, at the same time, I will say that there are some characteristics of life that at least are shared by all life forms on Earth. And those are, that life is made of cells, that there is a system that does metabolism, which means is able to harvest energy and materials from the environment and use them, that there is this information system that is capable of transferring, properties and so on from one generation to the next. And also, there is some catalysts, that are capable of doing chemistry in a more efficient and faster way.
You mentioned some of the ingredients as being an energy source, liquid solvent, nutrients is critical for understanding life. And on the current planet that we live on Earth, we have unicellular organisms, we have multicellular organisms such as ourselves. When we start to think about life generally as having a variety of ingredients or characteristics, is that something that we would try to see elsewhere in the universe, on other moons, planets, exoplanets as well? Or are those things just, for whatever reason, unique to life here on Earth, is how we think about it?
Yeah. So, we don't start by thinking that things are unique to Earth, in the sense that we do know from very detailed astronomical observations, for example, that the same laws of physics and chemistry that happen here happen actually probably throughout the entire universe. I mean, we see even, galaxies that are 10 billion light years away from here, and they still seem to be governed by, the light we get from them and so on, by the same laws of physics that we have here. So in terms of the laws, they all appear to be the same. Now, in terms, in terms of how things develop, there of course could be differences from one place to another. Most of the current searches for life elsewhere try to detect simple life or simple biosignatures, simple signatures of life in the atmospheres of these extrasolar planets, for example. There is a different parallel attempt at finding what we call intelligent or complex life, and that is typically done by all kinds of radio emission and things of that nature, or optical emission. So there are these parallel efforts to find different types of life. Also, there is another line that tries to find life in our own solar system. For example, on Mars or on Venus. And as you know, just a couple of days ago, the Europa Clipper was just launched to Jupiter's moon Europa. So also on the moons that revolve around the giant planets, Jupiter, Saturn, and so on.
So, this is kind of a general fun question of sorts, but I think a good one in some ways is, are we alone? Do you think that, what is if there are similar ingredients here within our solar system or in the universe, is it likely, not necessarily intelligent life per se, we can talk about that later, but just the idea of life in this very general way of defining it, is it likely there is life or organisms on other planets or moons or exoplanets?
So, of course, it's likely, perhaps. The thing is that I cannot really answer that question. And the reason is the following. You see, we have advanced a lot in the last few decades. So, for example, we know that our own galaxy, the Milky Way, may contain maybe even as many as 1 billion sort of Earth-sized type planets that orbit their stars in what we call the habitable zone, which is that Goldilocks zone that is neither too hot nor too cold to allow for liquid water to be on the surface of a rocky planet. So we know all that. And then many people come to me and say, oh, with all these billions of Earth-sized planets in the habitable zone, it's not possible that there isn't life elsewhere. Well, I'll tell you what, it is still possible. And the reason I say this is the following. We have no idea what is the probability for life to emerge, even if all the conditions are right. Because we so far have only one example of life, which is here on Earth. So we don't know what is the probability for the emergence of life. We don't know if life is inevitable in a way, that if you have the conditions, then life must appear, or if it's a really fluke chemical accident that, we just got very, very lucky for it to appear. So because we don't know that probability, even if you tell me that there are trillions of planets out there, I don't know at this point in time that the probability of life emerging is larger than 1 in a trillion, for example. So this is why I cannot actually answer this question, and this is why it's worth finding. The thing is, if we don't search, we will certainly not find anything. So we have to search.
So you worked at Hubble for a long time. Now, many people will know about the James Webb telescope that's been out, and I think it was maybe 2 years ago or last year or this year. There's always a new round of images coming from very high resolution images from different galaxies. Um, I mean, I think some of the newer ones more recently were the spiral galaxies, which, I mean, don't even look real. It looks like someone painted it. Like it's like, wow, that's a real thing out there in space. It's incredible. What's the, I guess, importance of, I think there's like the nominal importance of like, yeah, let's just take pictures, let's see what's going on. But more than that, like what is something like that, a very powerful telescope that can look as far as we've possibly maybe been able to see. What is the necessity or the real tangible thing about why that telescope in sending those pictures is important, and what kinds of data can we extrapolate from just those images alone? What is the significance, I guess, of that?
Yeah, so the James Webb Space Telescope, of course, will contribute to all areas of astronomy. But just to mention two, because you mentioned galaxies, and on the other hand, we're talking about life.
Mm-hmm.
So let me just concentrate on those. What can it do in terms of galaxies, in terms of life, and so on?
Mm-hmm.
So in terms of galaxies, because James Webb works in infrared light, and because our universe expands, and therefore all light is kind of stretched, and even light that when emitted was, let's say, in optical range, it turns into infrared when we see it. We can see very deep into the universe, to the very early stages of the universe. And we can see at some level, perhaps almost the very first galaxies that appeared in our universe. We see the universe when it was a tiny fraction of its current age, and we see the very early galaxies in the universe with James Webb. And that means that, we can tell how, well, at least some things about how the first galaxies formed, and, later about the evolution of these galaxies. So that's on one hand. In terms of life, what we really try to do is determine the composition of the atmospheres of extrasolar planets that revolve around other stars. And James Webb, Hubble started offering to us some such things. You see what happens if you have a star and the planet that revolves around it. And if our line of sight happens to be in the orbit of that planet, that when the planet goes in front of its parent star, light from the star, some light of the star, passes through the atmosphere of the planet on its way to us. And there, it is absorbed and so on, or scattered by the elements that are in that atmosphere. So that's how we can tell some things about the composition of that atmosphere, and therefore we can tell whether or not there are some things that are indicative of life. And James Webb is better than any telescope that we had so far, including Hubble, in trying to characterize in this way the atmospheres of extrasolar planets. Now, there will be hopefully something that has been called the Habitable Worlds Telescope, to be launched maybe around 2040 or thereabouts, which will do this job even better than James Webb. But at the moment, the James Webb Space Telescope is the best we have to try to characterize the atmospheres of exoplanets and to tell us whether there are signs of life there.
It's very, very helpful. It's very, very fascinating. Tell us real quick about this Goldilocks zone, and the habitable zone. Earth is in one of these, right?
Of course.
It's not too hot, not too cold, not too far away.
We are here.
So, we are here.
The fact that we are here to talk about this means that it is.
Right, that's right. But in other places in the universe, we know that there are other Goldilocks zones as well. Could you tell us about what do we see similar or different in each of these habitable zones?
So, in the solar system, Earth is in the habitable zone. Mars kind of marginally so, and Venus barely so. So this is that region. It's like an annular region. It's like a ring of distances from the parent star, where the temperatures are not too hot nor too cold to allow for liquid water to exist. If you come closer than that, it's too hot. You get steam instead of water, liquid water. You got farther, it's frozen. So you want a place where there is liquid water, because liquid water, we think, is the best solvent to try to help life emerge. So we are looking for, in the search for life elsewhere, we're looking especially for planets that are in the habitable zone. And we found many. There are lots now, even in the Milky Way, lots of planets in the habitable zone. For example, there is a system known as TRAPPIST-1, which is a star. It's a smaller star than the sun, so the habitable zone is closer to the star because the luminosity of the star is much lower. But it has 7 known planets, and 3 of those are in the habitable zone of that star. So those were very, very good candidates to look for signs of life in them. Unfortunately, at the moment, we find that those probably don't have an atmosphere at all. Because, small stars like that, they have all kinds of eruptions and things, and mass ejections and flares, which can remove the atmospheres from planets. And also, because the planets revolve actually much closer, they generate, if the star has a magnetic field, they generate currents in the atmosphere which heat the atmosphere and they lose the atmosphere. So they turned out to be less promising than we originally thought. But there are other cases. There is a planet 55 Cancri, for example, which is found to have an atmosphere. So we are starting to find planets that have atmospheres. And like I say, we try to determine the compositions of those atmospheres. So far, again, the planet I just mentioned does not have a particularly promising atmosphere for life. But the fact that we can even determine that it has an atmosphere and what it's composed of is already a big step forward.
Before I get to some of the chemistry, biology parts of the book, I do want to ask, I've talked about it briefly, I think, elsewhere here, but this idea of how life formed, again, it's kind of a long story, I think, but maybe you just give us, from your point of view, how we understand how life, or how Earth was formed, how that happened, and this idea that life may be formed from the vents on the ocean floor and things like that, where we started to see these, cellular kinds of organisms. How do we first start seeing, quote unquote, life here on Earth in the beginning, or the main hypotheses of what that is?
Yeah, so let me just say that we, namely Jack and myself, we actually are not great believers in life having started at hydrothermal vents at the bottom of the ocean.
Why so?
We actually think that life most probably started in small lakes or ponds on the surface of the Earth.
Interesting.
And the main reasons that we don't think that hydrothermal vents, it is certainly true that hydrothermal vents at the bottom of the ocean are currently populated by lots of life forms. But the fact that they have been colonized by life does not mean that that's where life started.
Sure.
And some of the main reasons we think that it couldn't have started there is that, well, first of all, well, first of all, nobody has shown that there is a plausible path from chemistry to biology at hydrothermal vents environment. Second, the experiments that have been done for origin of life have shown that you need high concentrations of the key materials that you need for life to start. And at the bottom of the ocean, it's very difficult to get high concentrations because everything is diluted and lost away. A third reason is that it turns out that in the early processes of life formation, ultraviolet radiation from the early sun probably played a very important role, but such radiation does not penetrate all the way to the bottom of the ocean. So again, in our opinion, I'm not claiming that all researchers agree with us, but in our opinion, hydrothermal vents at the bottom of the oceans are not the birthplace of life, but rather small lakes and ponds on the surface, which, interestingly, it is precisely what Darwin himself thought. Even though he had no idea at the time, he kind of said, well, maybe it started in a warm little pond, and so on. And we now think that he was probably right.
Yeah, we're still doing Darwin's homework and Einstein's homework. We're still doing it, hundreds of years later. It's wild how brilliant those guys were. So you spent a lot of time in the book talking about the importance of RNA and ribosomes, and then also talking about amino acids and peptides. What are the, when we think about these kind of building blocks for life and the certain environmental contexts that are necessary, could you tell us about why these things are so essential for understanding kind of the fundamentals, I guess, of life and the bits and pieces of it?
Yeah. Yes. Here, look, for many years, origin of life researchers had the following stumbling block. When you look at current life, modern life, you see that everything in life depends on everything else in a circular way. Meaning, there is this situation where if you want to form proteins, which are, of course, important part of life, you need DNA today to actually do that, DNA and RNA to actually do that. But to form DNA and RNA, you need enzymes, which are proteins. So there is a serious chicken and egg problem, which for many, many years, really was an enormous obstacle that nobody knew how to get around. And then, in the late last century, people discovered suddenly in the 1980s or thereabouts that RNA actually can also work a little bit like an enzyme, like a protein enzyme. So RNA can be the chicken and the egg in a way. It can even catalyze its own production. So RNA became, like people started thinking, maybe life could have started just with RNA, because RNA could do both the role of, storing information and moving it around, and as an enzyme to catalyze chemical reactions. And this led to this concept of the RNA world, that the early life on Earth was all governed by RNA. This is why RNA is considered so crucial to all of this. Now, amino acids, they are simply the building blocks of all proteins. All the proteins that we know about of life are made of about 20 amino acids. So whatever mechanism you find for the origin of life, you need to be able to produce RNA and you need at some point to be able to produce the amino acids that are the building blocks of proteins.
You mentioned, and others have mentioned as well, the importance of cells. And we've seen this, for a while was genes, 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 genes. But it really is cells that are, they're all important, of course, but cells also have a really big role to play as well. And in the book, you talk about protocells and then these modern cells. You also talk about spatial localization as well. Tell us about these protocells and modern cells and why cells are important for life on Earth.
Yeah. Cells are important for many reasons, but let me just give two important reasons. First of all, you need to keep all the key players in one place for them, not to spread around, and because then they cannot do anything. So, of course, this compartmentalization is necessary. But it's more than that. You need the cells for Darwinian evolution, because what does Darwinian evolution tell you? It tells you that if you have, say, an enzyme that can do the work better, then okay, you want to give it the opportunity to do its work better. But if you let it drift away, it will not do anything. If you keep it inside the cell, then it can do for you, or for this cell, what you need. So that's the importance of cells. Now, modern cells, the cells of today, they do lots of things, and they have a very complicated membrane, which things can pass through it, and other things cannot pass through it, and all that, and so on. The early cells, or the protocells, they were probably much, much simpler entities. They were something like a simple membrane inside which there were some pieces of RNA or something like this that started doing its thing. So this is how cells probably started, and then later, they slowly evolved to the kind of cells that we see today.
So when we piece all these things together, we see that we were able, obviously, to get to different types of organisms. And so this is maybe, I don't want to over centralize Earth, right? Obviously different planets or places have different ways maybe, but would we expect to find some of these similar building blocks on other planets, even in other galaxies, as long as there's a star and there's enough for heat and there's liquid and there's all these things? Would we expect to see versions of cells and RNA and of course we don't know because we haven't been there, but would we, in terms of modeling it, would we expect to see a similar structure, or would it look different, or we don't know?
Well, like I say, until we actually find something, we don't know. But
sure.
But if you have an exoplanet, a planet around another star that is in the habitable zone of its star, which means that it has liquid water on its surface, and presumably it may have had similar starting materials like what Earth had, then in principle it could perhaps do everything else that happened on Earth. But at the same time, for example, we see that Mars, let's say, which was formed from almost the same area of the disk around the sun that the Earth formed from. And today today there is no life on Mars. We think that maybe there was some past very simple life on Mars, and hopefully we will even find it someday, after we have more landers and so on Mars. We hope to find them. But the fact is that the conditions there did not allow for life to evolve like they have had on Earth. And in the case of Mars, for example, this is most probably for the following reasons. Mars is smaller than Earth. Smaller bodies lose their heat faster, and so because their surface area to volume is larger, so they lose heat faster. And also they are not so able to keep their atmosphere on. Mars hardly has any atmosphere today. So it lost almost everything by the time it was about 1 billion years old. So there are all kinds of tiny differences in conditions which make it hard to predict whether or not life will emerge or not. But certainly the early conditions could have been in many places.
Mm-hmm. It's interesting, right? Because Earth, as far as we know, was and looked and felt different in the early stages in formation, billions of years ago. 2-3 billion years ago, it was a different planet. I mean, it was, maybe, is it possible that, Mars is something like that? It's at its current state now, but maybe in another million years it will be different and maybe it will be more habitable, or hard to say?
No, I think in the case of Mars, it will not be more habitable. Well, it will be more habitable if we will get there and be there, then it will be inhabited, of course.
Yeah.
But not on its own, probably.
Mm-hmm. Yeah.
If anything, Mars was more habitable early on. Maybe 4 billion years ago, life could have been, some simple forms of life could have started. In fact, I would be amazed if life did not start some 4 billion years ago on Mars, but probably never got very far.
So, in terms of the planets in our solar system, Mercury is out of the question. Venus is unlikely as well. Mars,
unlikely, but not out of the question, because a few years ago they claimed to have found phosphine in the upper atmosphere of Venus, and this is a substance that on Earth at least is formed by bacteria. So now there are missions now planned to go to Venus. They are called Morning Star missions, and they will find out if indeed there is phosphine and whether that gives any chance of. It's not life on the surface, but maybe in the atmosphere. On the surface of Venus, it's very hot. Because there is a strong greenhouse effect on Venus. So lead would melt on the surface of Venus. So it's not now not particularly So Mars is a good possibility. Venus a little bit less, and then there are these several moons around the giant planets, Jupiter and Saturn. There is Europa. There is around Saturn. There is Enceladus. There is Titan, which are known to have large liquid water oceans underneath the surface. Now, as I said, I don't think life would have started there, because I don't think life started in large oceans. But if, for example, a rock was thrown out from Mars, and that rock contained some early life forms, and it hit Europa, then, maybe that life could be sustained in that ocean. So this is why, it's important to investigate those moons.
Yeah, it seems like they're more likely. There was news recently about, kind of going, instead of Mars, going to Europa, which is known to have a kind of a liquid body. But I guess explain, because from Mars to Jupiter is far, and definitely from Earth to Jupiter is far. So we're talking about a moon that's orbiting a massive, massive, massive planet like Jupiter. If it's so far from the sun and it's out of the quote unquote Goldilocks zone, how do we suspect, how are things able to kind of survive there? You mentioned in the book tidal heating as one explanation of this. Explain this first.
Heating. Yes, tidal heating. We feel the tidal force of the moon, for example, of our own moon.
Yeah.
How does that work? Okay, so you have Jupiter and you have, let's say, Europa, which orbits it. Okay, if you look at the line that connects, let's say, the center of Jupiter to the center of Europa, then along that line, there is a point on Europa's surface which is closer to Jupiter than the center.
Mm-hmm.
And there is a point which is the farthest from the center of Jupiter along that line. Okay, what happens is in the closest point and in the farthest point, there are tidal forces. The planet is being stretched a little by the gravitational force of Jupiter. This is called the tidal force. Okay, and this, if the moon moves, let's say, in a somewhat elliptical orbit, which means that sometimes it is closest to the planet and sometimes it's farthest, then it's this stretching, it stretches and eases, and that creates a friction, internal friction, which generates heat, and that heat can keep water liquid underneath the surface. So Europa, for example, has a thick icy layer at the surface, but underneath all that ice, there is liquid water. And similarly happens, let's say, in Enceladus, in Titan, and so on. So it's not because of the energy coming from the sun, which is in the normal habitable zone, but in energy that comes just from the tidal force of the planet around which they revolve.
Does that indicate, or could that mean that you could have sustainable life on those moons from tidal heating alone because of the friction that's created from such a large mass like Jupiter or Saturn, or hard to say?
Well, it's not that from the tidal force, because of the tidal force, you have the liquid water ocean.
Mm-hmm.
And the liquid water ocean, if you were to bring life there, it
Mm-hmm.
could perhaps be sustained in that liquid water.
Mm-hmm. Interesting. Wow. Do we see this in other places? So you talk about in the book exoplanets. So maybe you could explain to us the difference between a planet and an exoplanet. Maybe this is a little bit too
No, an
too
exoplanet is
particular.
just a planet around a star other than the sun.
Okay.
That's it.
So what makes exoplanets appealing in the search for life, right? And you can talk here about biosignatures, gravitational microlensing, direct imaging, etc. What makes them so attractive for people to explore there?
Well, we have our own solar system, and in our own solar system, we have Earth on which we know there is life. So we are looking for other stars around which there are planets.
Mm-hmm.
And if there are planets that are in any way kind of similar to Earth, in the sense that both in terms of their size and in terms of them being in the habitable zone, then those are obvious candidates for places to search for life. And that's basically what we do.
On exoplanets, what are the materials we're looking for? You mentioned an ozone layer, methane, water, molecular oxygen. What are we looking for?
So we are looking for things that will convince us that they could only be created by life and not by just some simple chemistry. And that means, for example, essentially all the oxygen in Earth's atmosphere was created by life. When Earth was formed, its atmosphere contained no oxygen whatsoever. So the atmosphere was created by all kinds of algae and bacterial life, and it grew to the point where, oxygen is today's some 21% of the Earth's atmosphere. So if we were to find a planet around another star, and we could determine that its atmosphere contains some 20% oxygen, that would be a very, very suggestive candidate for a planet that has life on it. Now, this would not be enough in itself. I mean, it will not be sufficient evidence, but it would certainly be indicative evidence And then we would want to look for something else too. In particular, we know that the atmosphere on Earth is not in thermochemical equilibrium because of the life processes. So, for example, you cannot have in a stable situation where in the atmosphere you have oxygen and methane, because they would destroy each other. Only because there is a continuous supply of oxygen from life on Earth, you can maintain such an equilibrium. So if you find an exoplanet that has an atmosphere rich in oxygen, which also has methane, that would be a very strong candidate for harboring life.
Do we have any exoplanets now that have
Not
those
yet.
ingredients?
No, not yet. No.
So that's why we keep looking, right? That's why we keep
Right.
we keep looking. It's out there somewhere. So this idea of intelligence, you mentioned in the book the Drake equation and other things, but we've been talking about life kind of very loosely and generally, but it starts getting a little bit, I guess, harder of sorts to see intelligent life. Well, what do we think about that, about intelligent life out there somewhere? What are the thoughts on this?
Yeah, you see, the fact that I told you that we still don't know if there is life anywhere else, we know even less about the possibility of having intelligent life. Because if we look even on Earth, where there was life, we realize that the evolution to very complex life, or what we call intelligent life, dependent on all kinds of contingencies. Just to mention one, about 66 million years ago, an asteroid hit the Earth, and that led to the demise of all the dinosaurs.
Right.
Now, the dinosaurs, were very large, but pretty stupid. So, so had that not happened, then maybe there was no what we call intelligent life. And by that I mean like a technological civilization. It is very unlikely that the dinosaurs would have developed a technology. So because there are these extra accidents that have to happen, we really don't know what is the probability for intelligent life to emerge elsewhere. In addition, we have other problems to deal with. For example, some AI gurus will tell you that AI type machines are going to take over and dominate intelligence on Earth in not too long. Some of them dare to say even just in a few decades. But you know what? Let's suppose they are off by a lot, and it will be 1,000,000 years. That in 1,000,000 years, AI type machines will be the dominant species on Earth. 1,000,000 years is nothing compared to evolution. Evolution on Earth. Earth is 4.6 billion years old. So 1,000,000 years is nothing. So it is not impossible. I don't know that at all, but it's not impossible that if that is true, that if there even is intelligent life in, let's say, in the Milky Way galaxy, it is all dominated by machines. And those machines may be superior to us by so much that, we are like ants to them. And, what kind of communication do we try to have with the ants in our own world? So they may even know about us, but they are completely uninterested in us because they know that we are ants.
Yeah, it's an interesting perspective of like, what do we potentially have to offer if they're a higher form of intelligence? We might not be very interesting. So it's an interesting piece of that. I guess the other thing which becomes, is more, I guess, popularized of sorts, and we mentioned it briefly in the end of the book, is the aliens, the UFOs, as they're now known, the unidentified aerial phenomenon. I actually think that's changed too. It's there's another name because there's some footage that's been released by I think the Pentagon about the craft is going underwater and coming back up and underwater. So they've changed the name. It's not just in the air, things like that. What do we? We have increasing reports of this. There's always another whistleblower that comes out every 6 months or whatever. There's a few people testifying in Congress. There's always a big reveal, and it's sort of kind of anticlimactic. I mean, should we take this stuff serious? I mean, it's always, it's fun to kind of think about. But I mean, on the hard science of this, what should we make about this?
At the moment, I would say up to now, I've not seen any reason to take this seriously. That means I've not seen any type of even semi-convincing evidence that these things represent alien life. Now, this is not to say that all phenomena have been fully explained. I mean, but there are many phenomena that, given that we have only limited data, we cannot explain. That doesn't mean that these are alien things. I mean, in the 1950s, most UFO stories used to come from, I don't know, farmers in some remote places, things like that. Now, this has advanced to the field of Navy pilots seeing some strange things. Things like that. But I have not yet seen any convincing evidence. And there is a famous saying by Carl Sagan that extraordinary claims require extraordinary evidence. And so we really need extraordinarily convincing evidence that this is the case. And I've not seen yet. At the same time, let me say the following. I'm all for, searching, for example, for various artifacts that may even be here on Earth that maybe indicate the possibility of such things. There has been a suggestion of, some meteorite that fell, that there were some spherules that were formed, that maybe they came from an alien spacecraft or something like this. Again, I did not find that particular claim convincing, but at the same time, I'm all for these types of searches because, as I pointed out, if there is an alien very intelligent, much more than us, civilization, if we just look for such things like radio signals, well, radio communication may be something completely archaic for them, and they don't use it at all. On the other hand, artifacts, are there, and if they are not destroyed, you will find them. So, I'm all for trying to search for such things, but I have not yet seen anything to convince me that we have found something.
In terms of kind of, what are we currently looking at? So we mentioned some of the landers and rovers on Mars. We mentioned some of the Webb telescope. We've mentioned, going to exoplanets, things like that, or moons. But in terms of the science, where is the emphasis in a variety of multidisciplinary approaches, chemistry, biology, physics? My understanding and reading of this is some people still look for the grand unified theory to connect quantum mechanics and general relativity, but outside of that, it does seem that there is a emphasis on dark energy, dark matter, and trying to understand that. But what would you say are the kind of current spaces that people are trying to understand things about our universe we don't know, and what the future looks like for research in physics and things like that?
So you mentioned some of the big problems in physics. And I've been involved in some studies of that kind, about dark energy, a little bit dark matter, and so on. Those are big problems. And indeed, there are extremely talented people working on those. But I'll be honest with you. If you ask me what I regard at the fundamental level as the most interesting or intriguing problems in science, in fundamental science, I would say they all revolve around origins. Origin of the universe, origin of life, and origin of consciousness. Now, we have made enormous progress on the origin of the universe, with a variety of telescopes from the ground and in space. We know, for example, that our universe started from a hot, dense state that we call a Big Bang. We don't know everything about what happened there, and we not exactly sure how inflation worked, an early period of very rapid expansion and things like that, and how did the universe actually tunnel from being nothing into actually being a universe or a space-time and so on. There are many unsolved problems there, but we made a lot of progress on understanding the origin of the universe. We made a lot of progress in understanding the origin of life. Things, for example, we mentioned that what do you need to know? You need to know how did RNA start? How did amino acids start to make the proteins? And how did cells start? How did you make membranes and so on? From these three main problems, we know how to make two of the four nucleobases of RNA, so half of the building blocks. We know how to make 12 out of the 20 amino acids that form proteins. And we know how to make very simple membranes, unfortunately not close yet to what modern membranes look like. So again, a lot of progress. Probably, at least to my view, the least progress has been made on the origin of consciousness. We have AI machines today, but they are not conscious. And nobody knows whether consciousness is an emergent property, which if the system will be complex enough, it will emerge by itself, or it's something that will never emerge, in which case machines will be able to do lots of things, but they will be what philosophers call zombies. So these to me are the main things. Now, you mentioned various problems in physics. Lots of people are working on them. Unification of gravity with quantum mechanics, a big problem. We had great hopes that string theory will do it. It was the best candidate to do it. So far, it has unfortunately failed to produce predictable results. So we're not convinced that it's the right way of going. But I'm sure that if we find the right way, some of the things developed in the context of string theory will prove very useful. In terms of dark matter, let's say, there are many searches for dark matter all across the globe, in the US, in Europe, and so on. They have failed so far to discover the particles of dark matter, but those particles have more than 10 orders of magnitude in energy to hide in. So it's not easy. So, I don't know if anytime soon we will find anything along those lines. Understanding dark energy, there are new things. I mean, there are some hints that maybe dark energy early on it sort of was different than what it is now, things of that nature. But we still don't know. So on all of those, people are working on. But I told you what I regard as the three questions that mostly intrigue me.
Yeah, I think that's right. I like the way that you kind of frame it is these origins of the universe and life and consciousness. And yeah, the consciousness question is certainly a big one. And
yeah, there are other things obviously in physics. So I do agree, much like the book models, and as you describe, a multidisciplinary approach is probably the best thing to try and understand and tackle these important big questions. Mario, this is so much fun. I really enjoyed talking with you about physics, about your work, and about obviously the wonderful book. So I can't say enough thanks for you coming on and giving us your wisdom and your knowledge. It's much appreciated.
Thank you very much for having me.